So before resuming where I left, I forgot to tell you a story. I said I would say something about Riemann. I forgot about, right? I said something about Gauss and then started this general blah blah. So the second one, the Gauss's memoir basically was the starting point of differential geometry, as it is, the first one. But what really revolutionized geometry and laid the foundations for modern differential geometry was the second memoir by Riemann. So this on some hypothesis on the foundations of geometry, which lie at the foundations of geometry. That's what this means, right? Which is which, Uber is on. So there is a story behind this memoir of Riemann. This is what is called the, I will resume this thing after my story about Riemann. Okay. So this work was what was called the habilitation shrift of Riemann. So this was in Germany. So after you finish your PhD thesis, before you get a degree, you have to submit another thing, another thesis kind of another work, which is called the habilitation shrift. So this has to be in an area totally different from the topic of your thesis. Okay, so Riemann's thesis was on complex function theory, right? That's where the Cauchy-Riemann equation, Riemann surfaces, and all those things. In fact, the complex function theory, usually three people are the most important, the basic complex function theory, Cauchy, Riemann, and Weierstrass, right? Cauchy always used integrals, Weierstrass always used power series, Riemann used geometry. They introduced Riemann surfaces in that context, which in a way started modern geometry also. What I have been talking about here, what are called manifolds that I'll come back to. But anyway, so for the habilitation shrift, what you have to do is, what one has to do is suggest three topics on which you are going to give a write-up, thesis kind of thing. Totally different from the topic of your PhD thesis. So of the three titles that the candidate gives, the examiner will choose one. Okay? And so the candidate has to write up a thesis on that topic. So Riemann gave three topics. The first two he was fairly familiar with. Last one was he gave was Foundations of Geometry, of which he had not thought about anything. He didn't know. The examiner was Gauss, so, so Gauss chose the third one. So Riemann had to write down a thesis on geometry. So he worked for several months and came up with one of the most seminal treatises on mathematics. So that is this. On hypothesis which lie at the foundations of geometry. So in that he came up with a very general kind of geometry in arbitrary dimensions. So far, even until the time of Gauss, geometry was done only in space, R3, right? Curves and surfaces in R2 or R3. So Riemann's geometry was in arbitrary dimensions. And you see, as long as you are in R3 or R2, you already have have many things, many tools available to you. Length of a curve, right? Distance, so on. So Riemann introduced a very, very general form of geometry on a general kind of space. Space is what we have been trying to formulate just before the break, okay? And so he came up with what is called now as the Riemannian metric. If you look at even in R2 or R3, how do you define the length of a curve, for example? Once you have a parametrized curve, alpha t, so what is the length of alpha? Alpha is defined on some interval, say C1 continuously differentiable or some regular thing. Then you define the curve as the length as AB or 0, 1, whatever. Right? So what is inside is alpha prime is what? The velocity vector, if you like, or the tangent to the curve, the point. So the length of the tangent vector is what is inside. So Riemann came up with the idea that, I mean, the way of defining such a thing, for example, in a very general setup. What you need to define this, how do you define length in Euclidean space? Basically, length of a vector x is given by the dot product or the inner product, the usual dot product. So on any Euclidean space, there is a natural length. So this is nothing but, in R3, for example, if you have this, is nothing but square root of that, this length. We are going to study some of these things a little later, okay? So you have a curve, you have a tangent vector, and you want to measure the length of the tangent vector, right? In whatever space you are looking at. So how do we compute the length of the tangent vector? For that, what we have is some inner product on the tangent set of tangent vectors. Okay, that's what we have in our setting in R3 or any Euclidean space. So what Riemann did was to introduce So for example, if you have a surface, right, on each point of the surface you have a tangent plane or whatever, tangent plane, let's say in R3, right? So on each tangent plane, you introduce an inner product, right? Just to measure the lengths of this tangent vectors or velocity vectors. So you see, in this case, everything is, if you are working in a surface in R3, you already have an inner product in R3 that is the same everywhere on points of the surface, right? So if your surface is not sitting inside a Euclidean space, okay, there is no, a priori you are not given any inner product. So what Riemann did was to introduce a concept of an inner product on the tangent space at each point of the surface. So of course that has to be in a smooth way, right? So when you go from one point to the other point, another point, the metric, the inner product here and the inner product here must be related in a smooth way. Of course that can be made precise, we'll come to that anyway. So that is what is called a Riemannian metric. Metric here is not the usual distance function, right? It is a smooth way of defining inner products on tangent space at all points of the surface. Of course, it does give rise to a metric in the usual sense, a distance function later on. That's another point. But metric here, to start with, refers to a smooth choice of inner products on the tangent bundle, that is tangent space at each point. More or less, change the whole face of geometry. So there is no restriction on the dimension, okay, no restriction on anything. So very general, no Euclidean thing coming in. So you can have geometries which are not Euclidean geometries. Of course, Gauss himself had discovered non-Euclidean geometries earlier. And then, of course, two other, Janos Bolai and Lobachevsky, two other people also had discovered. Gauss never published his findings, but they were first published by a Hungarian mathematician called Bolai and a Russian mathematician called Lobachevsky. Anyway, so non-Euclidean geometry is very different from Euclidean geometry. So in other words, Euclidean geometry is only one of a very huge collection of geometries. So for example, Riemann's geometry was what was needed for Einstein when he formulated the theory of relativity. What was needed in the theory of relativity was not Euclidean geometry, Riemannian geometry, where you have actually you don't have a Riemannian metric, but what you call as a pseudo Riemannian metric. You don't have an inner product. It's not positive definite. It's not even positive, right? So just a bilinear form. Okay. So anyway, so much of what Riemann did had a huge impact on further development of geometry in the next, until now even, I suppose. So, see, Euclidean geometry, you are able to talk of many things, right? Lengths, angles, this, that. So all those things are not possible unless you have a Riemannian metric. So geometry that you do are all on what are called Riemannian manifolds. So what I have been trying to talk about are what are called manifolds. So manifolds with an additional metric structure called the Riemannian structure. So the astonishing performance from Riemann, just a couple of months, he came up with something very profound. And Gauss himself was very happy about the Riemann had to give a lecture on that also to Gauss. So, so Gauss himself apparently was very happy the way Riemann had done the whole thing. Gauss is not usually appreciative of people in general because Gauss essentially knew everything, more or less. Okay? So, but he was himself very impressed by what Riemann had done. So that was a great thing for Riemann. The Gauss was already at that time a legend, and Riemann was just an upstart at that time, so to say. So Riemann was very afraid, but he did very well, and Gauss himself was impressed. Okay, so the Riemann, let me just say one more sentence about Riemann. Riemann published very little, but whatever he published was seminal. It started the whole branches of mathematics. Each one of them started the whole branch of mathematics. So he basically, other than he had published something in physics also, but in mathematics, he published something on complex function theory, that was his thesis, and then he had the complex, the geometry habilitation strip, and then he had paper on Fourier series, where he first introduced what you call as the Riemann integral now. In his work on Fourier series, only he introduced his integral. And then he wrote a paper on the zeta function, what is now called the Riemann zeta function. It is probably one of the most important function in modern number theory. So everything Riemann did had a huge impact on mathematics. Okay, so coming back to where we left. So just to recall, what were we trying to do? Trying to formulate something, get hold of some spaces on which differentiability will make sense, right? So for that, we were trying to look at spaces which look locally like Rn. So the obvious way to try is to say that f is differentiable if the composition of this with the homeomorphism here, so that you get a function from the disk or Euclidean space to R. That is differentiable. But then there is a problem. What is the problem? There may be another neighborhood, another homeomorphism to a ball, right? If you are going to base your definition only on a single choice of that homeomorphism, that's not going to be well defined, right? It should not depend on the choice of homeomorphism that you make. I may give one homeomorphism, you may take another homeomorphism. So the concept of differentiability should not be changed. It should not depend on the person that is doing things. So you need put some restriction, right? Some condition to prevent the definition from depending on the choice of the homeomorphism. So the right condition is that, suppose, let me draw a separate picture there. So suppose this is your point. So you have a homeomorphism from here to something here. You have a homeomorphism from here to something here. Okay? But you want to get something independent of the choice. So what you do is, of course, both are neighborhood of the same point. So the intersection is certainly neighborhood. So on this intersection, this homeomorphism is defined, and also this homeomorphism is defined, right? So what do you assume? So the condition that you want is F composed with this homeomorphism or F composed with this homeomorphism, either both are differentiable or both are not differentiable. If one is differentiable, the other is also should be differentiable. That only then, right? Differentiability, definition of differentiability will make sense. So we are trying to define. You want to say that F is differentiable if the composition of F with this homeomorphism is differentiable. So if your definition should not depend on the choice of the homeomorphism, it should be differentiable with any other homeomorphism also. When does that happen? If you assume, so you have a homeomorphism here, so we are working on the intersection now, right? So in this case, you can start from here to here. So this somewhere here, so you can come back to this. That is, start with homeomorphism, go to the patch on the surface, use the other homeomorphism to come back to Rn again, right? So you have pieces of Rn here, you have neighborhood of the point on the surface. So you have a homeomorphism here, homeomorphism here. So if you start from a patch on the sphere, on the surface, okay? So you can come like this to one part of the Euclidean space, go back via the same part. Now, of course, you restrict to a smaller piece, namely the intersection. So if you assume that this composition, that is phi, if you call one of them phi, the other is psi, if you assume that phi composed with psi inverse is differentiable, then right, whether this is going to be differentiable if and only if right? If you assume that this is differentiable, then what is going to happen? This is differentiable if and only if this is differentiable, right? That's what we do. So in other words, so what are we trying to do? We're trying to just transplant a piece of the surface to the Euclidean space, right? Okay, so the way you transplant will not matter as long as the way you go from one piece of the Euclidean space to the other space is differentiable. So this is, what is this map? So this starts from one piece of the Euclidean space that you have here and goes to, so this is a mapping from a part of the Euclidean space to Euclidean space. So you know what is meant by differentiability there. So these are what are called transition functions or change of coordinate functions. Okay, so basically what are you trying to do? You're trying to basically give coordinates for points on the surface. How do you give coordinates? Go to the Euclidean space, look at the coordinates there. Right? If your point is P, look at phi of P. Phi of P is a point in Rn, so it has the usual coordinates there. If you have another way of going to the Euclidean space, psi of P will have another set of coordinates, right? But what you are saying to say is the way you go from the coordinates of phi of P to coordinates of psi of P is smooth. If you ensure that, the whole thing is going to be independent of the choice of the homeomorphism. The way you go from patch on the sphere, patch on the surface to Euclidean. So, but there is a terminology that we used here. Probably we'll come back to this and say a little bit at the end of the course. So any space on which such a structure is there. What structure? First of all, we have a space. Space means what? a topological space. Okay, and then the first condition is this, and the second condition is this looks like should not depend on the way you look at it. Okay, that's what the second condition says. The way you go from one, see, what does this look like do actually? Transforms a piece of the surface to a piece of the space to a piece of Rn, right? Another choice will do a similar thing from another piece on the surface or the space to a piece of Rn. So, in a neighborhood of a single point, the assumption is that which way you go, you do, whether you choose this choice or choose this choice should not matter. That's all. Right? That's all the condition is. Which translate to saying that maps like phi composite psi inverse. Phi is one homeomorphism from a neighborhood of P to Euclidean space. Psi is another homeomorphism from another neighborhood of P again to Euclidean space. So when you compose phi composite psi inverse, so this is a mapping from a part of the Euclidean space to Euclidean space itself. So if this map is smooth, there is no problem. Everything is fine, right? That's the assumption. So such a structure, a space with these two, satisfying these two conditions. Locally, it is like Rn, and the transition functions or coordinates functions are smooth. These are the two conditions. Okay? This what is called a manifold, or a smooth manifold, in this case, differentiable manifold. So these are the proper geometric objects on which you can try to do some geometry. But when you want to talk of lengths or angle and such things, you need an additional structure that would come from a Riemannian metric. That will essentially not talk about, but maybe we'll mention it somewhere towards the end of the course. Okay. So such manifolds are called Riemannian manifolds. Smooth manifold with a Riemannian structure, that means a smooth choice of inner products on the tangent space at each point. You will see what the tangent space is soon. So you have the Riemannian geometry that way. So this is general differential geometry and then Riemannian geometry. So this way, so these objects are abstract objects, right? But modeled after Euclidean spaces, locally, right? Locally, manifolds, differentiable manifolds are abstract spaces modeled locally on Euclidean spaces, so that you can talk of differentiability. So for example, Rn itself is a differentiable manifold, or a sphere is a differentiable manifold of dimension 2, so on. Okay, so dimension doesn't matter here. What we are going to do is, in a very specialized setting, like surfaces in R3, for example, a sphere or a hyperboloid, a cylinder in R3. So even here, I mean, what is the advantage? This makes life enormously simpler, because so we don't have to worry about differentiability. It is already there because you have the ambient space R3, or the Euclidean space is there. You have the ambient metric. You already have inner products everywhere, so we don't have to worry about inner products. So everything is there already, just because we are sitting in a Euclidean space. So that gives a first simplification. And even further simplification we are going to have by assuming that we are going to look at only hypersurfaces, meaning surfaces which have one dimension less than the ambient space. That means what you usually call as surfaces in R3, two-dimensional surfaces, what you usually call as surfaces are two-dimensional objects, right? So surfaces in R3 are in general n surfaces in Rn plus 1. So this again gives a lot of simplification because we can talk of normal straight away to the tangent plane. Otherwise, this orientability becomes a nuisance in general. So as long as you are in setting of a hypersurface, everything is a lot simpler. Okay, so that's what we are going to look at. Of course, most of the examples will say n surfaces. You might have already used the term like hyperplane or hyper subspace in a vector space. It just means that one dimension less than the whole ambient space. Of course, so this n surface means an n-dimensional surface in Rn plus 1. What is meant by dimension there, we'll come to that. But most of the examples will be two surfaces in R3, ordinary surfaces. For example, a curve in R3, the curve is one-dimensional, right? Whatever it means. So a curve is one-dimensional, so we are not going to talk of a curve in R3. Right? It's not a hypersurface. Of course, we have to talk of curves on the surface. That's a different thing. For that matter, we are not going to talk about geometry of curves at all, just to save time. Okay, we are going to look at only surfaces, but necessarily we have to look at curves on the surface to study geometry of the surface itself. So, what is a surface? There are a number of ways we define an n surface. Essentially equivalent, some convenient for some purposes, the other convenient for other purposes, and so on. So let's see. So give me an example of a surface. R3 is good enough. Some surface. Give a name or give an equation or whatever. Give a parameterization. Some surface you know in R3. A surface, an example of a surface in R3. Huh? Sphere. Okay, so what is a sphere? Okay, fine. Is there any other way of looking at the sphere? We heard of polar coordinates, spherical polar coordinates. Inner. Spherical coordinates. Somebody? Spherical coordinates? Make a start. Say something and then we can add more. You see, just like look at the circle, right? We'll come back to the sphere. Okay? So you usually write in R2, right? Circle as x square plus y square equal to 1. But you also write it as right parametric equation. Theta going to cos theta sin theta, right? So similarly, you have for the sphere also, right? Spherical coordinates cos theta, cos phi, cos theta, sin phi, sin theta, something of that kind, right? So there are at least two ways of describing a sphere, for example, or a circle. One is in terms of a parameter, right? A parametric equation, if you want to call it. The other, this one, is what is called a level surface, meaning you have a function x, y, z, all points x, y, z satisfying equation f of x, y, z equal to some constant c. So in the case of the sphere, this is f x, y, z is x square plus y square plus z square, c is 1, if the radius is 1. At least now you have two ways of saying what a surface is. One is a level surface. The other is parametric surface, if you want to call it. As a definition, you can take any one of them, doesn't matter actually, because both are equivalent in some sense. At least locally, they are equivalent. I'll come to that. So let us take, let's give one definition and then see that it's the same as the other thing locally. So let us take the first one as the definition, for example, to start with. Okay. So how do you define a level surface? You have a function f, right? But when you say a function, you have to specify the domain and specify the codomain and say what kind of function it is. Right? So we will work always in the smooth category. That means we will assume that everything is smooth, right? Function and surfaces, all things are smooth, meaning infinitely differential. That makes life a lot simpler. So if you look at this example, this function is smooth, okay? No problem with that. What about its, if you look at f of x, y, z, what's the gradient of this? Of course, we will define the gradient later on, but so what are the partial derivatives, for example, if you look at of f, you are going to get 2x, 2y, 2z. Okay. On the surface of the sphere, not all of them can be 0. Right? 2x, 2y, 2z. If all of them are 0, x, y, z are all 0, but the constraint is x square plus y square plus z square equal to 1. So on the sphere, at least, that is on any point of the sphere, at least one partial derivative is non-zero. Okay? That means the rank of the Jacobian is 1. It's non-zero. That's what's needed. Okay? So you say that such a point is a regular. You use the term regular as long as the gradient does not vanish. So what do you have? You have an open set You have a smooth function on the open set, and then you are looking at the level set of that function, right? Of course, you see, this this constant, you can actually, if you want, you can absorb in the function itself. If you want, you can write it as fxyz equal to 0. Take c to the other side. Call gxyz as fxyz minus c. So what concept you put here doesn't matter actually. You can change the function. So for us, what is an n surface in Rn plus 1? Is a level set all points where f is equal to c, you write as f inverse c, right? Where, so you have to specify what f is. F is a smooth function defined where? So first of all, specify the domain, open, f is smooth, and at least gradient is non-zero at each point. That means at least one partial derivative is non-zero at each point on the surface. At least one is non-zero. Of course, from point to point it can differ, right? At a point P, the first one may be non-zero. At another point Q, the second one may be non-zero. So at every point, at least one of them is non-zero. So usually we call it as a regular surface. A regular n surface is like that. For us, everything is. I'll dwell upon this a little bit more later, but give examples and so on. But let me introduce tangent vectors before going further, because tangent vectors may be needed for the afternoon class. Okay, I don't know, but anyway. So you have a surface, all right. How do you define a tangent vector at a point on the surface? I'll come back to this definition again later. Even on the sphere, how do you define a tangent vector? Take a point on the sphere. How many tangent vectors are going to be there at a point? Right? But at least one. So what is a tangent vector at a point? How do you define it? So you have to go back to curves. Right? So take a curve lying on the surface, and assuming that you know what is meant by a tangent vector to a curve, right? So you take suppose this is your surface, okay? So you have a point on the surface. So what you do is you take a curve lying on the surface, passing through that point P, and take a tangent vector to that at that point. Of course, at the same point, you can have any number of curves. Each curve will give you one tangent vector, maybe the same, maybe different, right? B at P to S is alpha is a curve, smooth curve in S passing through P. So what do you mean by this? Alpha is a curve in P, smooth curve in P, smooth curve in S passing through P. So first of all, what is a curve? Alpha is defined on some interval whatever Rn plus 1 in our case in general. But you're saying a curve in S. That means the range of alpha should lie in S. So that means alpha t is in S for all t. Right? Passing through P means for some t naught, alpha t naught equal to P. Okay? And then the velocity vector or the tangent vector at that point is alpha prime t naught. So you want to talk of smoothness. So smooth as a function into R3, Rn plus 1. Because we don't know what you mean by saying smooth into S. Right? You have the ambient space, ambient Euclidean space. That's what you are going to use. So you have a function taking values in Rn plus 1, a smooth function, but actually the range lies on S. That's the condition. So this is what is meant by saying a smooth curve in S. So this just says it passes through P and the tangent vector at P is P. But in practice, it's always convenient to take the interval to be an interval containing 0, right? And take this t naught to be 0. There is no loss of generality in that. You can always translate the interval to get an interval like this. So if you want, you can write this, then that instead of taking 0. But usually you take it to 0 just for simplicity. Tangent vectors at a point are tangent vectors to curves passing through that point. That's all. So what can you say about the set of all tangent vectors at a point, at a given point? They form a vector space. I will come to this point. Actually, I have I need to say something there, but I will come back to this later. So geometrically, if you look at, so here is when this hyper comes into the picture. If you look at the sphere, for example, at any point you have a normal, right? Namely the radial vector. So the tangent plane is going to be just the plane through that point perpendicular to that normal vector. So this is true in general. So the gradient is always going to be orthogonal to the tangent vector. We'll come to that. Okay. So these tangent vectors, these play a very important role in the whole business. Okay. So these are very important to understand. So we'll stop now, and when we start again, we'll come back to the definition of surfaces and look at some examples, and then come back to tangent vectors again. Okay.